Okay, so good morning. I will be explaining to you the first order reaction today. There's some construction outside, so it might be a little bit noisy in here, but it's a proper time to discuss this. So what we're going to discuss today is the first order reactions. Order of reactions. There. This PowerPoint was made by Nina Quinagoran, my partner in this activity. So first things first. In order to understand how to determine the order of a reaction, we must first know the meaning of rate law. So let's define it. Rate law for any general reaction occurring at a fixed temperature. So if the temperature is not fixed, then the rate varies because the value of K varies with the temperature. So rate law states that with this equation, rate law states that rate is equal to K, A raised to M, B raised to N. And this can actually be extended further. So it could be C raised to another letter and then D raised to another letter. The point is, each reactant has its own order. And if it doesn't affect the rate, then it is a zero order reaction, which will be discussed later. So next. Okay, so the value of K is the rate constant, which is a specific rate constant is specific to a specific temperature. So A and B means that it is the concentration of the reactant. So it's the moles per liter of each reactant. So during an experiment, A and B varies while K remains constant, and of course the orders remain constant. So as these two vary, it will have an effect on the rate of the reaction, which will be explained further later. And the exponents of M and N are the reaction orders determined by the experiment. So if you go back, these are the reaction orders. So for example, the concentration is 2M, and then from 2 it becomes 4, so it doubled. If M is, for example, the order of the reactions is second, then it will affect the rate by a factor of 4 and not by a factor of 2 because it is squared. 2 squared is 4. We know that. And then we move on. Our reaction has an individual order for each reactant. So each reactant may vary with its order. Okay, the reaction is zero order with respect to the reactant if the reaction's rate is independent of the concentration of the reactant or does not change whatever the concentration of the reactant may be. So, the reaction is first order with respect to the reactant if the reaction's rate is directly proportional to the concentration of the reactant. So, later, I'll edit this. The reaction is second order with respect to the reactant if the reaction's rate is directly proportional to the square of the concentration of the reactant, just as what I explained a while ago. In the zero order reaction, as seen by the graph, the concentrations of A doesn't really affect the rate of the reaction. That's what I was trying to explain a while ago. While here at the first order reaction, while the concentration of A rises, the rate also rises with it. So there's a direct effect. While for a second order reaction, it has a parabolic nature. So as A increases, the concentration, the rate increases at a parabolic manner, at an exponential manner. So how do you determine the reaction order using the reaction rate? So we inspect the exponents of the reaction values in the rate law, not the coefficients of the balanced equation, to find the individual orders. We add the individual orders to get the reaction order of the law. So here in this example, based on the rate equation, the rate law equation is that the order of NO is second while the order of H2 is 1 because it's raised to 1. So if we add both of them, then the order of the whole reaction is raised to 3 because 2 plus 1 is equal to 3. Note that the reaction is first order with respect to H2 even though the coefficient of H2 is in the balanced equation is 2. So here in the equation, H2 was 2. See there, it was 2. But in the rate law equation, it's not raised to 2. Just because the coefficient of H2 in the balanced equation is 2, it doesn't mean that the order of that reactant is 2. In this example, it is 1. So here for the second example, the reaction order is first order with respect to H2O2. It is also first order of reaction with respect to I, as seen here in the equation. So first order. And with respect to H, you might be asking, why is it not here in the rate law equation? It is there. It is H plus raised to 0. So 0, anything raised to 0 is 1. And then if it is 1, then it's not there in the equation. But it's still there, if you know what I mean. To reiterate my point, even though it is a reactant, as seen there, it is not really a factor in terms of computing for the rate because it is a zero order reaction, which a while ago it was defined that the concentration of a zero order reactant doesn't affect the overall rate of the reaction. So this places H plus to have a zero order. So we just look at the coefficients of the reactants in the equation, really. 1, 1, and then the overall reaction is 2 because 1 plus 1 is 2. And then H2 is non-existent there, but it's there. It's 1. It's raised to 0. So how do we determine the rate of the reaction when the rate law equation is not given? So reaction orders must be determined from experimental data. It cannot be deduced from the balanced equation. So we do not rely on the balanced equation to find out the rate of the reaction. We have to get experimental data, which will be shown later, to determine the orders of each reactant. So I will explain later. So to determine the values of M and N, which are the orders of the reactions, we run a series of experiments in which one reactant concentration changes while the other is kept at a constant. And we measure the effect on the initial rate in each case. So let's move on. So here, just to explain, this is all experimental data. We know all the rates and we know all of the concentrations. Now, here's the equation to solve this. What we just did is, the first equation is rate 1 is equal to A1 raised to M times B1 raised to N. And what we just did is we divided that with another rate law equation. So rate 2 is equal to A2 raised to M and B2 times B2 raised to N. So combining both of them, we can simplify it to rate 1 over rate 2 is equal to A1 over A2 raised to M times B1 over B2 raised to N, as seen here. Now the problem is, there are two unknown variables, M and N. We already know the rates as shown here, and we already know the concentrations of A and B as shown here. So what we really don't know is M and N. So how can we simplify this? We can remove N by making this 1. So let me explain. For example, we take experiment 1 and 2. What's going to happen is, so 3 times 10 raised to negative 2 divided by 3 times 10 raised to negative 2 is 1. 1 raised to anything, even 0, is 1. So taking that into account, we simplify the equation into this. Because B1 over B2 is already 1. We already know that despite not knowing what N is, what the order of B is. So once we get this equation, we can just plug in the values and see the value of M because we have only one variable missing and we know all of the rest of the values. And if you don't know B, then you just do it again. You find two experiments which have the same A right here. Experiment 1 and 3 or 2 and 4 have the same A. Now because they have the same A, it means that we can assume that this is 1. This thing that I'm pointing at. And then we can simplify the equation into rate 1 over rate 2 is equal to B1 over B2 raised to N. and then we can get the value of n. So really, it's just about knowing what you don't know, m and n, and then plugging in the value so that you could remove one of the variables. Now, the exception of this is that there isn't an experiment where the concentration of A or B is kept at a constant. Now, to solve this, you have to know the value of n, because if you know the value of n, then you can just plug in the values and just solve it anyway, because there's only one thing missing. If m could be the only thing missing because you already solved n a while ago. That is an alternative. Oh, that is an alternate solution to this kind of problem. For example. So again, thank you. I hope you learned something. Please leave a like and please perfect us for explaining this beautifully. And as you can see, this PowerPoint is the best. I don't know what to say. Bye-bye. See you next week on Peter Teaches You Chemistry. Bye. Yeah.